Hello, welcome on my YouTube channel. In this video I'm going to guide you through a tutorial on GDAL that is available at the GIS OpenCourseware platform. GDAL or GDAL is a translator library for raster and vector geospatial data formats. It also comes with a variety of useful command line utilities for data translation and processing, and that's what we are going to investigate in this tutorial. Starting with GDAL 3.11, parts of the GDAL utilities are available from a new single GDAL program that accepts commands and subcommands. In this tutorial we will use this new GDAL command line interface. After this tutorial you'll be able to retrieve information from GIS data, reproject GIS data, change raster properties, convert raster formats, convert vector formats, apply spatial queries on vectors, convert comma-separated value files and perform batch processing. For this tutorial you need the files from GIS OpenCourseware and QGIS installed on your computer. The easiest way to type GDAL commands is through a terminal from QGIS. In the browser panel, go to the folder where you've saved the data for this tutorial, click right and choose Open in Terminal. There you can type commands. You can see that the prompt is already at the folder where we have our files. If you type GDAL and it responds like this, it means GDAL works. Let's use the dir command to see what files we have in this folder. We have shapefiles, comma-separated value file and a geotiff. We also have a folder with land use data. Let's start with retrieving information from GIS data. We can use the GDAL info command. Let's apply it to the SRTM elevation model that we have here. And this is the result. What we can see here is the size in rows and columns, projection information with EPSG 4326, so this is in the geographic coordinate system, the pixel size, and here at the bottom I can see which data type is used, integer 16, and the no data value. Each command is well documented. You can find it under Programs, GDAL Application, and in this case raster commands, although that's not so clear. I'll explain why. So here we have GDAL raster info, but remember that we've used GDAL info. So you can also look for GDAL info. The search works really fine. Here I have GDAL info. And if I click on it, I see that it acts as a shortcut for GDAL raster info or GDAL vector info depending on the nature of the specific dataset. This means I can also apply this to vector data. So I type GDAL info and I'm going to use it for the roads data. And here I see the result. It's a line dataset. It has also geographic coordinate system with EPSG 4326. And there are some attributes there. Let's also use it for the other shapefile that we have in the dataset. And this is a polygon dataset with EPSG 28992. And here I see the different attributes. GDAL info also allows me to see the feature information. So I use GDAL vector info -- features. And I use that layer here, and then it will report to me all the features with their information. But that's a bit too much. So we can also look at a sample. So if I add here to the same command -- limit, and then the number of features I want to show, in this case 1, it will just show me that amount of features. And this gives a good idea about the data. As we've seen, some of our datasets are in the geographic coordinate system, so I'm going to use commands to reproject them. First the raster one, GDAL raster reproject, and if I use -d, I can give the destination projection, which is EPSG 28992, in this case the Dutch projection. Then the input file name and the output file name. With enter it runs. It gives a warning. Warnings are not errors, so it still performs. In the documentation we can find more information about how to use this command and have more control. But first I want to point out that we have used options with a single and a double dash, And here in the documentation you can find that single dash is often used for a short version and double dash for a longer version. If you want to specify the output resolution, we can, for example, use -- resolution and then give the X and Y resolution. Now we can easily open the file in QGIS to check the result. So there is dem_rd.tif in the browser panel, and if I drag it to the map canvas, I can see it there. In the same way, we can reproject vector data. Use the command GDAL vector reproject -d EPSG 28992. Then the input file name, roads in this case, and an output file name. And I'll also save it to a shapefile with the name roads reprojected. There it runs. Gives a warning about characters, but we shouldn't bother about it now. Also here in the documentation you can find more options. Next we're going to use GDAL to convert different raster formats. We use the GDAL raster convert command for that. Here you can find all the options and some examples. For example, how to convert to a cloud optimized GeoTIFF. I'm going to convert the GeoTIFF to a Saga file. I use GDAL raster convert -f to specify the format, Saga in this case, the input file, TIFF file, and the output file, the s.dot file. And we can open it in QGIS and compare it with the GeoTIFF and see that it's exactly the same, but with another format. Some formats need more arguments. PC raster, for example, needs a specification of the data type, if it's Boolean, nominal, scalar, or something else. So here I'm going to convert to a scalar PC raster format, and therefore I have to specify with --co that the value scale vs equals scalar. However, this gives an error, which means that GDAL is expecting a float 32 raster. When you have checked the information with GDAL info, you might have seen that the data type for our DEM is integer 16. Therefore, we first need to convert the data type of the input. I'm first going to delete the previous output because in QGIS I can see in the browser panel that it was generated. Now I'm going to use the GDAL raster set type command, and if I want to see the help I need to add --help, which is a quick way to read the manual. And there I see that I need the OT option and specify float 32. So let's do that. Give the input raster and the output file name. Here it gives an error that is clearly readable. I need to use double-OT. And there it runs. And now I can use the command to convert to the PC raster format. GDAL raster convert -f PC raster -co vs equals scalar, and then the input needs to be changed to dem_rd float that we just created, and then the output to the .map format, and now it works. Agila is a little tool that comes with PC raster for visualization, so here we can see the result in a special viewer. In the tutorial on GIS Open Courseware you can find the different options for the different data types. It's more efficient to run all these commands after each other and don't save the intermediate results. Therefore we can use GDAL raster pipelines. Let's first delete all the outputs we created. Some are locked because QGIS is still open, so best to do is start a new project and run the delete command again. So we're going to use the GDAL raster pipeline command to first reproject the original SRTM digital elevation model to the Dutch projection, then set the data type to float 32, and finally write the result as a PC raster scalar raster. Let's search for raster pipeline in the manual. And there we see that we need to have a read at the start, then we need different steps, and finally we need to write the result. So let's see how to construct this command. So after GDAL raster pipeline we need to read the input data. So we start with read. Then I give the SRTM GeoTIFF file that we have as an input. then each step needs to be separated by an exclamation mark. So the first step then is to reproject to the destination of EPSG 28992. After that step, I need to set the data type with setType --OT float32, and then an exclamation mark for the last step, which is to write the result to PC raster. And I need some options there, -F for the format PC raster, and --CO to specify that the value scale is scalar. If I press enter, the whole workflow is run without saving the intermediate results. And this is fast and efficient. Let's visualize the result with Agila. And we see that it's the same as we had before. We can also convert vector formats. So all formats that you can convert are found in the raster and vector drivers. And the short name is the one you use with the -F option. And what we're going to do here is convert the municipality shapefile to a Google Earth KML file. So I use GDAL vector convert -F for the KML format, then the input file, then the output file, and with enter it runs. It gives warnings for field type conversions, which it is not supporting, but here that's not a problem for us. Now we can visualize the result in Google Earth. Go to QGIS and click right on the KML layer and choose Show in Files, and there double click on the file to open it in Google Earth. This works when you have Google Earth already installed. And it now zooms to the layer where we see all the municipalities of the Netherlands. We can also use GDAL to do queries on vector data. We're going to create a map of Delft where we want to do the following analysis. We want to select the municipality of Delft from the municipality map and save it into a geo package. And then we want to clip the road map of the Netherlands with the polygon of the municipality of Delft. So first we're going to check which attribute in the municipality vector layer contains the names of the municipalities. We use GDAL info again. The attributes are in Dutch, but GM naam is a municipality name. So we need to use that attribute in our query. Let's check in the documentation on how to do SQL queries. There's the GDAL vector SQL command. And here we see some examples. So in our case the command would be GDAL vector SQL, then the input shapefile with the municipalities, then the output geopackage that we want to create. But we also need to then define the output layer that needs to be saved into the new geopackage, and we call the layer municipality. Then --SQL to give the query, which will be select * from, and then the name of the input layer without the extension, where, then the name of the attribute, GM naam equals, and then a string in single quotes, Delft. And we end this with double quotes because the whole SQL string needs to be in double quotes. It quickly runs and we see the result here in the browser panel, and I can drag the municipality polygon to the canvas to check the result. Now I want to clip the roads. I use GDAL vector clip. Here in the documentation you can find all the options. And I need to use --like to specify the data set and the layer. So that will look like this. GDAL vector clip. Input is the roads reprojected shapefile. Then the output is the geopackage that we created before. Therefore we need to use --update, so a new layer will be added. And the name of the layer to use for clipping also comes from that geopackage, so I use --like with the name of the geopackage, and --like layer with the name of the layer that we want to use for clipping, so the polygon of the municipality. And then I need to specify the output layer. That's a new layer to be saved into the geopackage. and that's Roads Delft. If I hit enter, the new layer is created and I can load it in QGIS. I need to change the styling a bit to make it clearer. I'm going to use green lines, and I can also add the elevation model that we created before. Reorganize the order of the layers. Let's style the DEM with single band pseudo-color and stretch the colors after we've chosen an appropriate ramp to the current canvas. It's also good to make the municipality just a boundary, so I choose a simple line and make it a bit thicker. Back in the documentation, you see that you could have also used a SQL statement that we've used before to select the municipality from the original municipality vector layer. Let's try that. So the command is GDAL vector clip. The input is roads reprojected. And I'm going to save the output to a shapefile just to have a difference with the previous one so we can compare them easily. And here I use for like the original municipality shapefile. Then I use like SQL to give the SQL query, which is the same as we had before. Select asterisk from, and then the name of the layer, where GM naam equals Delft. And then we run it, and we can check the results in QGIS by adding this new shapefile. And it completely overlaps with the previous result. When we hover our mouse over the layers, we can see what format they are and which projection they have. As with raster data, we can also create pipelines with vector data using GDAL vector pipeline. Because we can only read input data in the first step and write results in the last step, we are going to create two pipelines for what we want. The first step is to create a pipeline to extract the Delft municipality polygon. We read the original municipality layer. The next step is to do the SQL statement, followed by the step to write the result to a GeoPackage. I create a new one so we can compare the result, and the output layer name is municipality. So the result is in a new GeoPackage but with the same layer name. I get an error here because the name of the layer with the municipalities is wrong. I forgot to add the 1. And now it runs. I can check the result, and that's correct. So we proceed with the second pipeline, which is to reproject the roads, clip them to Delft and write them to the same GeoPackage. So read the roads. First step, reproject. The destination EPSG 28992. Next step is to clip. And we use data from the data GeoPackage, and the like layer is the municipality. And then the last step is to write the result also to the data GeoPackage with output layer roads Delft. And I use -- update to update the GeoPackage with the new layer. It runs. Let's check the result. We need to refresh the browser panel, and there we see Roads Delft added to the GeoPackage and exactly a copy of the other version we had. Now there's one thing we need to fix, and that's that we want to clip the DEM to the municipality boundary. And we can do that with GDAL raster clip, which is very comparable with GDAL vector clip. First we use like to identify the dataset, which is the data GeoPackage. Then like layer to define the layer name that we want to use for clipping. Then the format of the output, so GeoTIFF. Then the input file and the output file. And there's the result. drag it to the map canvas, and we can copy the style. And here we have our result. We also have a file with locations in a CSV file. It's good practice to first view the contents of a CSV file and to verify the coordinates and the column separator. The separator is not always a comma and sometimes depends on the language settings used while exporting from a spreadsheet program. We can view the contents by using the type command, or you can open it in Notepad. Here I see the contents. It is indeed comma separated, and we have latitude and longitude coordinates, which means that I have to use EPSG 4326, the geographic coordinate system. To change the projection of the CSV, we first have to create a virtual data source by creating an XML control file. We can do that in Notepad. We first need to identify that it's an OGR virtual data source. We can describe it by the OGR VRT layer name, which should correspond with the locations CSV data source. I use 3 spaces for indentation. With SRC data source, I indicate the name of the file. With geometry type WKB point, I indicate that these are points. With layer SRS, I identify the EPSG code of the projection used for the input, which means the coordinates in the comma-separated values file. With geometry field encoding, I indicate that there are points from columns, with X corresponding with the lon column and Y with the lat column. Then I close the tags. Save the VRT file in the location where you have your CSV file, so call it locations.vrt. And now we can use the GDAL vector reproject command with the destination projection of the Dutch projection 28992, as an input locations.vrt, as an output the data geo package that we already had, use --update to add a new layer, and --output layer to define the name of that new layer, which we call locations reprojected. And there I run it, and now I can open it in QGIS. Drag it to the map canvas, make sure that the points are on top, and change the simple marker to an SVG marker, for example. And I'm going to use a symbol, this one, and I make it a bit bigger. And with this one, it's nice to put the anchor point at the bottom. So the bottom of the pin is the location. That's already nice, but if you're curious what those locations are, it's good to see them in Google in 3D. So I'm going to convert them to a KML file. We learned that before, so GDAL vector convert -f, the format KML. Define the geo package with the input data and then the layer name with --input layer. And then the output file name. Gives an error because I made a mistake with the input layer, which is reprojected. And there's the result. And when I double click on locations, it will add those points to our Google map. And here we see the points. So there's the old church, the new church, and the city hall. And there's also IHE Delft Institute for Water Education. So desktop GIS applications are great for one-off operations, but they become inefficient when you need to repeat the same task for many files. In those cases, simple scripting can save a lot of time. In this example, we work with the dataset from a land use model of Dublin. You can find it in the land use folder. The rasters are stored in Idrisi RST format with one file per year from 1990 to 2030. Our goal is to convert all of them to the GeoTIFF format. So here I created a batch file, rst to tiff.bat, and basically it creates a loop around the files in the folder. So for %f means for each file that it finds in, and then the file extension rst, so it only looks for rst files, which is the Idrisi format, do, and then within the loop I write echo converting %nf, which means print to the screen converting, and then the file name without the extension. And then I add the GDAL command, GDAL raster convert to the format GeoTIFF, the input file name %f, and the output file is then the input file name without the extension, and then I add .tiff. I put the files in quotes so I can deal with spaces in file names. I close the loop with a bracket. And now when you run this batch file, it will apply the GDAL command to each file that it finds. And that's very quick and efficient. So here we see all the TIFF files that were generated. And this is much faster than doing this manually. So in this tutorial you've learned how to work with GDAL commands and convert, reproject and batch process vector and raster data.